Just as Nicholas Copernicus introduced the heliocentric model, another stunning revision of our understanding of the cosmos could emerge, sparkling a debate known as the crisis of cosmology. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope has put an end to this debate with an image that defies physics. So, what exactly is this crisis? And how does the James Webb Space Telescope contribute to it? Well, contributing to it is a bit of an exaggeration. It's more like a review that has been underway. But to put it in simpler words, crisis refers to a point at which our understanding of the universe is challenged, particularly in terms of its age and size, which are linked by a considerable margin of error. The introduction of the James Webb Space Telescope has been crucial in this context. Before this breakthrough, we were limited in how far we could see into the early universe. But with the JWST's improved capabilities, astronomers can explore much more distant galaxies, giving us new perspectives on the universe and challenging some of our previous conceptions. To understand the crisis in detail, it is important to review the standard model of cosmology, known as the Hot Inflationary Big Bang Model, or Lambda, CDM. This model has been very successful in explaining various features of the universe, from gravitational lensing to the structure of the cosmic web and the growth of galaxies. However, each new observation, especially with instruments as advanced as the JWST, raises the possibility that our current model may be incomplete or need to be revised. The description you give is about how the standard model of cosmology predicts the motions within groups and clusters of galaxies, as well as the characteristics of the cosmic microwave background as we go back in time. According to this model, galaxies should be smaller, bluer, less developed, and less rich in heavy elements, at cosmic distances greater than our own current observational range. This would lead us to expect to enter eras of the universe devoid of visible stars or galaxies. However, scientists have found contradictory evidence that challenges these predictions, resulting in a crisis in cosmology. The crisis in cosmology centers on the uncertainty about the age of the universe. Different measurement methods provide different results, leaving cosmologists struggling to reconcile these discrepancies. To try to address this problem, scientists use several methods to measure the age of the universe. One of them is the study of cosmic background radiation, which involves unraveling the history of the expansion of the universe and using mathematical models, such as the Friedmann equations based on Einstein's theory of general relativity, to determine the expansion rate, and therefore the age of the universe at different times. The cosmic microwave background, a residual radiation from the early days of the universe, is a crucial tool for this measurement. Detailed maps of the cosmic microwave background, such as those provided by the European Space Agency's Planck mission, offer valuable information about the composition of the universe. However, these maps lack data on dark energy, a major component of today's universe. Despite this limitation, scientists can use Friedmann's equation along with other observations to estimate the expansion rate of the universe at different times and ultimately determine its age. Another approach to determining the age of the universe involves observing exploding stars. While the cosmic microwave background provides a complete record of the composition of the universe going back billions of years, these historical records allows us to directly measure the expansion of the universe by observing its growth rate. We use Type 1 supernovae as consistent reference points, since we know their expected brightness. By comparing it to its observed brightness, we can estimate the expansion rate of the universe at the time of the supernova. This method, used in the 1990s, played a crucial role in the discovery of dark energy, which is now central to cosmological measurements. It is especially useful for determining the Hubble constant, which is a measure of the expansion rate of the universe. Although not exactly constant, the Hubble constant is instrumental in charting the expansion of the universe since the Big Bang approximately 13.8 billion years ago. It has been observed that the cosmos has been growing steadily, and NASA has noted that the implications of this rate are significant. If the expansion is slowing down, it suggests the presence of an unknown force, possibly dark matter, influencing this process. On the other hand, if the expansion rate is accelerating, it could indicate the presence of influence of dark energy accelerating the growth of the universe. In January 2018, scientists found something interesting. Although several telescopes indicated that the expansion rate of the universe varied depending on the point of observation, the Gaia Space Telescope measured a faster expansion in the nearby universe, while the Planck telescope measured a slightly lower expansion in the more distant regions of the universe. This discrepancy in measurements highlights the vast scale of the universe and reminds us of the pioneering work of Edwin Hubble, who first proposed the expansion rate of the universe in 1929. Now, considering the expansion of the universe independently of your cosmic location, you would witness the same phenomenon at the same speed as the Hubble expansion rate. Initial calculations were based on limited data, but with technological advances such as the Hubble and Gaia telescopes, we have been able to observe more variables and redefine our measurements. Other telescopes use readings of the cosmic microwave background to calculate the constant, although this method has its limitations due to the availability of supernovae for distant observations, which restricts our view of the universe. Since the discovery of dark energy in the 20th century, scientists have been puzzled by the discrepancies between these two approaches to the age of the universe and its expansion rate. As measurement technology becomes more precise, smaller variations arise, driven by the development of more advanced systems. This progress, ironically, raises more questions rather than providing definitive answers. Although the differences are marginal, with only 10 to 20 million years separating the estimates, given that the universe is approximately 13.77 billion years old, it still merits careful investigation. One possible explanation for this discrepancy is the possibility of flaws in our measurements of the cosmic microwave background. Despite being one of the most precise measurements, it has been extensively tested since its launch in 2013, validating its accuracy. Another perspective suggests a possible gap in our understanding of dark matter, raising the idea that it may vary over time and be related to dark matter or some other unknown factor. This possibility has led to numerous exploratory studies. The accuracy of supernova measurements is also questioned, as the complexity of star explosions can introduce uncertainty into the models we used. Resolving this uncertainty in supernova modeling could help resolve the discrepancy in measurements. This crisis in cosmology has been further aggravated by the discovery of the James Webb Space Telescope, according to Neil deGrasse Tyson. The JWST found objects in the universe that challenge our current understanding. This means that our scientific understanding needs a complete overhaul, but the problem is that we have no idea where to start. To understand the magnitude of this scientific apocalypse, let's look at the beginnings of the universe. About 150 million years after the Big Bang, stars, black holes, and star clusters began to emerge, possibly even as early as 50 to 100 million years later. However, these events should be relatively rare. What we don't know is how common galaxies evolved at later times, spanning events between 200 and 400 million years after the Big Bang. Recent JWST images reveal galaxies much more distant and therefore older than the standard cosmological model predicts. This discrepancy suggests that our model needs a significant update. The revelation that the expanding universe depended on galaxies is a fundamental innovation. JWST images show galaxies that formed much earlier than predicted by current cosmological models, triggering a crisis in the field. This problem is related to galaxies and redshift age, which is a common measurement in cosmology. According to the standard model, hydrogen began to appear 400,000 years after the Big Bang, when protons and electrons combined, leading to hydrogen recombination. This transformed the universe into a soft gas of hydrogen atoms with some helium and residual background. The gravity of the radiation then acted on small perturbation in this hydrogen gas, slowly collapsing them to give rise to the first stars. These early stars, composed primarily of helium and hydrogen, participated in nuclear fusion, creating heavier elements such as carbon and nitrogen. These elements played a critical role in galaxy formation by absorbing, heating, and emitting cooling protons, which facilitated the coalescence of gas into galaxies. If you liked the video, remember to like, subscribe, and activate the notification bell. Thank you so much for watching.